I'm James Coomer. It seems strange because we hadn't planned it this way at all. I saw those slides literally about 5 minutes ago. I'm the IME product manager, it turns out. And I've got a talk which is not covering the same kind of application topic, slightly different ones. But I did just change my slides about 5 minutes ago when I saw Carl's slides to add a bit more of a why and how IME is doing that stuff, because that probably puzzled people, and I thought I'd try and explain that in my talk. So, first thing is, there's various ways you can use Flash in a storage system to try and make your stuff go faster. And, either you can just spend all your budget on Flash. This is this one here. So, DDN does, we're known for large Lustre file systems or large GPFS file systems. And this IME thing is a relatively new concept. But, traditionally, you can either spend all your budget on these SSDs and stick them where your storage was, or you can do some kind of hybrid, which is some kind of caching approach, which is obviously sensible because then it means you don't spend all your money running all your storage out of SSDs. Today, that's still going to be expensive. And there's various methods for implementing a cache. And I'll talk a little bit about SFX and the L2 read cache within Lustre, and then I'll finish off talking about IME. So this is the general concept of the talk. How do we use Flash to accelerate workflows in a significant way? So before we start, we did some work, and I did want to present it, even though relatively briefly, with Paradigm. And we have some customers which run very large Ethernet environments. And what we wanted to do in this test was ask the question, what's the optimal job packing method for these Paradigm Echoes benchmarks? So we created a Paradigm benchmark which was both read-intensive and a write-intensive. In fact, a handful of different levels and types of read and write intensity. And then we ran these jobs on a fairly modest system. It's called a DDN SFA12K with Lustre, and we basically stacked up the number of concurrent jobs in the client to see where we hit the peak workload, and therefore we could advise customers about what system to use, the number of sockets, number of 10 gig or 40 gig links, and the relative trade-offs. So we can't dwell too much, we haven't got much time, but essentially what we saw here behind me is something around 8 or 10 nodes with a 40 gig link and a single node with 2 sockets is kind of an optimal kind of balanced budget choice for running multiple concurrent copies of a write-intensive Paradigm Echoes benchmark on this system. We did the same for reads, and there's, of course, quite a lot of read-intensive workloads on these things. We see a slightly different curve, but nevertheless, we see something between between 6 and 10 jobs per client we can run concurrently on the system. And by the way, we did stack this up to multiple clients till we saturated the system. So we saturated this particular system, which can do 20 gig a second, with about 30 of these nodes running this kind of stacking method. So this is kind of a little bit of background. So we got these intensive workloads, we stacked up the systems to find the optimal point at which we could run jobs per node. And then we tried to add a little bit of Flash. And I've just got one little number to show you later in a couple of slides. But we did this in a simplistic way. So as mentioned in the first slide, we've got several methods we can use to bring SSDs into the picture and see what results they're going to have. And of course, what we're trying to do is spend as little money as possible and get the biggest result as possible. And it turns out you get what you pay for. Who would guess that? So SFX is kind of the low-cost way. This is a kind of a controller internal magic. Pretty much every vendor has one. It's not very DDN specific, but you put some SSDs inside a controller, and what it does is this. When it reads and serves the I/O generally from a disk layer underneath, when it sees something which is accessed with small random reads that can be detected by the controller, it will then go ahead and serve that to the application, but then populate this set of SSDs. So that if they have a subsequent access to the same blocks, we can then serve them super fast from this little layer of SSDs, which then speeds things up. There's also a little API, see it over there. If you know what's going on in enough detail, you can actually just tell the controller to go ahead, I think I'm going to access this stuff really heavily, so go ahead and bring that into this SFX cache layer. And incidentally, so this is a controller level one, so we're not doing anything intelligent as an administrator. Not applying our incredible intelligence as an administrator. We're just putting some SSDs inside the system and letting the storage controller do its work. And the result for the optimal workload is this. We do 4K random IOs. So with no SFX, we get this number over here. When we add a bit of, essentially when we switch on SFX and read it twice on the second go, we get this huge hit. We get the benefit of the very large random IOPS capability of a small number of SSDs. So here I think we just see a handful of SSDs, like 4, relative to a fairly decent number of HDDs, about 60. And you can see just that small number of SSDs gives you a huge improvement in random IO. So the simple question is, how does that affect that previous workload? And unfortunately, I have just one number, because this is only part of the talk. So we do this strided read benchmark. We run this real code, which is based on paradigm echoes, doing read-intensive workloads. And the difference between SFX on and SFX off is around a factor of 3. For a small investment in a handful of SSDs, we get a huge speed up in this very particular sort of workload of read-intensive operations. But that's just a small part of the whole picture, right? So all we can do here is accelerate reads. What we want to do is accelerate the whole workflow. And there's my sort of major marketing slide. We've got 2 of these, I'm afraid. So IME, Infinite Memory Engine, is really a scale-out flash-native I/O system. So it's called an I/O system. It's a bit of a funny word. We just made it up. So that means it's not really a file system. It embeds within an existing file system just like Lustre or GPFS, or it could in principle be any other file system which serves out POSIX I/O. It's scale out and it's flash native. That means you have a number of servers, they can be distributed, they have NVMe or SSD of some sort inside them, and that comprises this IME layer. And then somehow, I'll tell you how, it embeds itself within this parallel file system. And today we support Lustre and GPFS. So this is exactly what Carl was doing before. He was logging into our benchmark center in Dusseldorf. We've got a little system there. We've got an IME system about this big with a bunch of servers. And he was running from a handful of clients through a bunch of servers, and there's a little GPFS file system at the back end. So what does it do, this thing? So really what it does is it provides this very different way of handling I/O. It provides a fundamental change in the way application I/O is handled. And this is really what this talk is about. Somebody better wave at me when you get to 10 minutes, because I'm going to run out of time. So what you probably don't know as an application developer is that all those constructs, all those rules you've learned in your application development lifetime have been, when it concerns I/O, it's been around attending to the niceties of file systems. So really, you're not doing something that's inherently good, you're just doing something that matches today's parallel file systems. And in particular, some of the constraints around parallel file system and how they work. So what IME does is it really changes that whole game. It's not handling small IOs in the same way. It's not handling files at all, really. It's using the back-end file system for that and handling IOs. And it's not moving the data between the compute nodes and the storage systems in the same way either. So everything's really radically changed, and that has an impact on how you can develop, what opportunities you have to do different things at the application layer. The other part, of course, the second statement up here is you meet the goals with less stuff. And that's less to do with the IME software magic. That's just because you're using SSDs. So we're getting 2 or 3 gigabytes a second out of something this big rather than 100 megabytes a second with an HDD. So it gives you a vehicle to implement large-scale flash within a parallel file system. But it does more than that. It gives you this fundamental change in how the I/O is behaving. Hey, you've seen this slide before. Let me drill a little bit deeper. So we've got this set of compute nodes, and we've installed an IME client. So it's got the Lustre client or the GPFS client, and on top of that, we've installed an IME client. What that's going to do is that's going to intercept the I/O coming from the applications through to the file system. So rather than going straight to the file system, the IME client grabs that I/O and sends it sideways into our burst buffer right here in the middle. Later on, it'll be tiered down to the parallel file system. So as far as the users are concerned, when they type ls or whatever, they kind of see their files and nothing's changed. It all seems pretty normal, but the fact is their I/O has been sort of fairly radically accelerated. And the other little funny thing about this picture is you'll see over here, we've got some little bits of colors in the I/O coming through here, and then we've got nice big bands of colors over here. So this is actually hinting one important thing about IME. We're handling fragments of data. So the I/O fragments that are issued from the applications, we're kind of handling them natively as I/O fragments and then placing them in SSDs and saying, right, it's safe, and acknowledging the I/O. A file system, of course, has to go through a rather longer construct before it gets to that status. It's got to take the I/O fragment and write it to the controller, probably read in the block, update the 4K fragment, write down the block, and then acknowledge the I/O. So we're not doing that stuff which you have to do in a file system. We're doing something very different and something a lot cleaner and faster. And then, as Carl mentioned, we do try and tidy up these fragments before we send it down to the parallel file system, so that even though your application might have been very bad and sent you many, many, many small random I/Os, we can send nice clean I/Os down to the backing file system as far as is possible. So here's the two kind of key elements in this picture. One, it gives you a scale-out flash layer, and two, it does something very different. It's performing random shared file I/O at wire speed, which is something a file system really doesn't do. So when you saw that 74x speed up, we've actually seen anywhere between kind of 1, like no speed up at all, and over 1,000x speed up, moving from Lustre or GPFS to IME. And when we get the 1,000, it's because we're tickling this particular pain point of a parallel file system, which is it's bad at doing random, particularly shared file I/O. And you do a lot of that in oil and gas. So how do we do that? I've got a couple of slides that kind of just peel one more layer back. So if Larry stops taking pictures, I'll carry on to those. So here we have the client side. A little bit more detail. So we've got the application at the top, and as I said, the blue thing there. We've installed this IME client. So we've installed some software, and that's sitting on top of the Lustre client. So we're overloading this Lustre client, and we're intercepting the I/Os. Now notice that metadata goes straight through over here. Metadata, file open, closes, stats. They go straight through to the Lustre client. So that means the look and feel of the system is just as it was. It feels like Lustre or GPFS. You type ls, you see your files. You type stat, you see your files, whatever. But when you do the I/O, it gets intercepted by the IME client layer and sent to these IME servers. And incidentally, we're kind of protecting this layer. So some burst buffers may not do this data protection thing. And so if you lose a server, you might lose your data for that run. We do a bit better than that. When we build the data, we also build parity. And we send that to different servers. So if one of these nodes dies, we can keep going and keep the production running without losing any data, of course. So this is actually an old run we did with iCheck. Oh, good, I did put the logo on. So this was a couple of years ago, some earlier on. This is reverse time migration code. And we ran the same code 3 times with a small, medium, and large data set. And it's doing this kind of very typical I/O pattern that we see in this sector quite a lot. So times along this axis, and you're starting off and you're writing chunks out to a file, or you're writing separate files, however you're doing that stuff. And then what that's going to do is if you've got a traditional cache architecture, you're going to fill up that cache, and then you're going to start reading it, and you're going to read it in the reverse order, which means that the last thing you wrote isn't necessarily going to be in the cache anymore. So you're only going to get benefit from like this portion here of sharing that data in the cache, and otherwise you're going to be fetching back to the parallel file system for these subsequent reads. So that's exactly what we're doing here. And the results, we've actually presented these before, but it's very pertinent to this crowd and IME. So in this case, what we're seeing is around, well, in the best case, it's not a very large case. Again, we're talking about testbed systems. With an 8.4 terabyte system, we're doing about a 3-fold speed up of the whole application run. That includes the I/O kernel, but it's a whole application end-to-end run. If we look at just the I/O times, then those are obviously much greater speed ups on the I/O times in of themselves. So here we see like maybe 8 or 9 times a speed up by you moving from a moderately sized Lustre system consuming about this many rack units to a moderately sized IME system consuming about half the rack units. So there's still some puzzling there. So how is it doing this stuff? And how real is this stuff? So how real? Here's the largest system we have today. This one's installed at JCHPC. It's a 1.2 terabyte a second system. So the largest file system in the world is something like 1.3, 1.4. This one's 1.2, but it's in about 2.5 racks. So it's very, very dense. It's a very large system. This is like number 6 on the top 500 list. And this one's a system that's in production. The really interesting number is actually over here. So if you could read this, it says write single shared file. So here, let's pause for effect. we're doing over 1 terabyte a second into a single shared file. So that's something you really can't do with a parallel file system, but we're doing it here with a benchmark. How long have I got left? I've got to check time. Who's managing my time? 4 minutes. That's okay. So this is just one of the problems you see, and Carl kind of outlined this again, so this should be straightforward for you. This is shared file optimization. So we do a lot of shared file I/O. We've got these huge, great shared files in this sector, and we do writes and reads into this big shared file. And that causes issues with parallel file systems because of the reason above. So what we see above is, on the top line, we've got some data in memory in the computers. The second little set of blocks down there is the file in the file system. And the problem is a parallel file system like Lustre or GPFS, for very good reason, uses a limited lock unit size around 4K. So what it does, if somebody says, I want to write something, it says, okay, here's you go, have this whole 4K, and do what you want with this 4K, right, to your heart's content, because you're going to get really good performances in your cache. The downside is that if somebody else wants to write a neighboring byte to the byte this guy wanted to write, then it needs to revoke the lock and get that 4K page back. And with these strided or even random shared file applications, what that happens is we contend on every single of these lock units for every I/O. So you can see up there, these processes are trying to write I/O in a strided fashion into a file, and every time they do that, they've got this false sharing problem. They're not trying to write over the same byte, that'd be crazy. They're trying to write neighboring bytes, but they happen to be within a lock unit, and so that has to invoke the locking process. The effect is right here. There's a benchmark that does just this. Very similar to a lot of what we see in this sector, is all these threads come along here, and these are the various threads running along vertically. The y-axis here is the start of the file at the bottom and the end of the file at the top, and then time's going along here. So what's happening here is all 20 threads or whatever are going to come along, try to write a byte into the first section of the file, or access the first section of the file in some way, and one thread is going to win and go racing off and do all his writes, and everyone's going to locked out until it's ready. And then one poor thread who's last is going to have to wait 100 seconds or whatever until it gets its turn. So what we do with IME is we don't do this 4K page thing. We deal in byte-level I/O units. So we don't have this false sharing problem, and so we can remove this intense locking mechanism from the system and now allow these parallel applications to run extremely fast. Just skipping a few slides. So here's just one more little taster before we hit the last slide. I've got 2 minutes left. So we do a few things which are rather differentiated. It's not just about performance. There's all the other stuff, how you treat the SSD devices so that they live a long time and don't degrade their performance. It's how you manage the system in real production use. On that latter point, we've got this quite a nice feature here, which is, again, unique to something which you couldn't really retrofit this to an existing parallel file system because it's too hard. What this picture is explaining is that when things go wrong, the system will cope and minimize the performance decrease due to that thing going wrong. So the red line here, what's actually happening is we've got a number of IME servers, and every 15 seconds, we're pulling one of the cables out of one of these IME servers. It's got 2 links. Then we're plugging it back in again. And we're waiting a few seconds, we're plugging it in. So every time we unplug it, the performance goes down, the red line here. Then we plug it back in again, performance goes back up. Unplug it, and plug it in. Now that's because all we've done is taken 4 servers and we reduced the performance of one of them by 1/2. But because it's a parallel file system, or working like a parallel file system, the whole performance of the whole system has dropped by 50%, because it's working at the speed of the slowest component. With IME, we've got this rather clever, dynamic, real-time, I/O, adaptive framework. We can just say, oh, this guy's going a bit slowly now, let's change the I/O path and send it over to these servers who are still running at full speed. And that's what the blue line does. The clients are measuring the I/O queue lengths on the servers, and if one goes high, it'll just change its mind and redirect the I/O to different servers. So the blue line shows a decrease in performance directly proportional to the amount we've actually taken away by unplugging that cable, about 1/8. So this is quite a nice feature, and it's one of maybe 4 or 5 we can talk about in some detail around IME. I'm going to finish there. So let me say that there's very good reason and technical detail behind why we see these quite incredible numbers sometimes for random I/O and shared file I/O. But that's not all the story. We've got a big improved efficiency with IME and a lot of different benefits which we'd like to talk to people about. Thank you.
Any quick questions?
Very nice results there. Could you say a couple of words about how this compares and basically, in a sense, tries to supersede the traditional I/O forwarding frameworks that like the big national labs developed, et cetera, and so forth?
Yeah, so if you've got two networks, right, and, oh, are you talking about burst buffers or just like a Cray architecture?
Burst buffers, like your stuff versus the, like what Argonne did, what...
Yeah, okay. So what we've done, I'm going to have to keep it very short, is create a very sophisticated global address space which runs on distributed flash. So nobody else has done that. So everybody else essentially, I mean, it's a bit more sophisticated than this, has essentially created a mechanism for moving data in and out of an SSD which is probably local, although it might be somewhat shared. What we've done is create this new sort of I/O path to a different address space across a distributed tier of SSDs. That's probably about as short as I can make it.
Thanks very much, James. Thank you very much.
Thank you.